We're starting chapter 3 on integer factorization and RSA, which is the most important, most widely used public key crypto system. And it's based on number theory. So you recall Diffie-Hellman and the El-Gamal systems were based on the difficulty of computing the discrete logarithm. So you have a prime p, a primitive root g, and you want to find the logarithm of some number a to the base p to the base g mod p. That's the discrete logarithm. And it's hard to do. No one can prove that it's hard to do. It's simply that the accumulated experience of many people for many years has failed to find an effective algorithm, an efficient algorithm for solving the discrete logarithm problem. The RSA public key crypto system is based on something different. It's based on the difficulty of factoring a positive integer into a product of prime numbers. Now, for small numbers, it's not hard. You can do it by hand or on the computer. For example, if I give you the number 1001, you can factor that. I think that's 7 times 11 times 13. But for big numbers, it's hard. And in particular, if n is a number pq, and even if we know is a product of just 2 primes, p and q, to factor n, to find p and q is hard. Again, there's no proof that it's hard. It is the fact that many people for many years have tried and failed to come up with an algorithm to factor an integer n into a product of primes. So, for example, in section 3.1 of the text, a number that appears is let's see, that's a nice number that pops up there. N equal to 64,349. In principle, and I'm telling you, this is a product of 2 primes, and you know that. But what are the primes? In principle, because this is a fairly small number, it's only 5 digits, you could work it out in an hour or 2 by hand. On my old computer using Maple, I can factor it instantly. It factors into 229 times 281. So if you let P equal 229 and Q equal 281, and you multiply them, you get this number N. But N only has 5 digits. If N had 1,000 digits, there's no computer exists in the world today that could factor that number in less than 100 million years. This can't be done yet. People are trying to build something called quantum computers, which in fact could factor numbers of that size. But no one is anywhere close to building a quantum computer yet. So the difficulty of the RSA public key crypto system is based ultimately on the difficulty of factoring a number into a product of primes. So that's what this lesson and the next lesson are about, sections 3.1 and 3.2 of the text. And again, it starts with some basic number theory. So let's recall Fermat's little theorem. It said if P is a prime and A and P are relatively prime, then A, the power of P minus 1, is always congruent to 1 mod P. So if P doesn't divide A, then you raise A to the power of P minus 1 is congruent to 1 mod P. For example, if you take P equals 7, let's say A equals 5, then P minus 1 is 6. And this says that if I take 5 to the 6th power, that's always congruent to 1 mod 7. I mean, this is actually quite a remarkable discovery, because there's absolutely no reason to think that 5 to the 6th power, if you take away 1, you get a number divisible by 7. That is, 5 to the 6th is 7 times some number d plus 1. You might calculate 5 to the 6th, subtract 1 and factor it, and see what you get. Actually, I'm rather curious. So let's see. I will compute. I'm going to make it 5 to the 6th is 1565. We'll check. 5 to the 6th is 15,625. 5 to the 6th minus 1 is 15,624. If I factor that number, 15,624, I get 2 cubed, 3 squared, 7 times 31. So this is equal to 7 times d, where d is 2 cubed, 3 squared, 31. And this is just an instance of Fermat's little theorem, which is always nice to see. But we're going to be, so this is what we know. What we're going to be interested in is something about what can be said about powers of numbers, not modulo a single prime, but modulo a product of 2 primes. For example, suppose you take m equal to 15. Can we say that a to the 14th, that's m minus 1, a to the m minus 1, that's a to the 14th, is congruent to 1 mod 15? that ever true? Yeah. Let's take an experiment. Let A equal 2. So what is 2 to the 14th? Let me just calculate this quickly. So 2 to the first power is 2 mod 15. 2 squared is 4. 2 to the fourth, actually, no. 2 to the fourth is 1. 2 to the fourth is 16, which is congruent to 1. So 2 to the 12th is 2 to the fourth cubed, is 1 cubed, is 1 mod 15. So 2 to the 14th is 2 to the 12th times 2 squared. 2 to the 12th is 1 times 4. This is congruent to 4 mod 15. 2 to the 14th is not congruent to 1 mod 15. So even though 2 is relatively prime to 15, it is not true that 2 to the m minus 1 is congruent to 1 mod 15. So this statement, let me just cross it off. That statement is false. If you start to experiment, suppose you take numbers that are relatively prime to 15. Let's see, 2 to the fourth is congruent to 1 mod 15. We just calculated that. 3 to the fourth, there's 3 to the fourth. No, 3 is not relatively prime to 15. So we don't want to consider that. 4 squared is the same as 2 to the fourth is congruent to 1 mod 15. 7. 7 squared is 49. Which is congruent to 4 mod 15. So 7 to the fourth is 7 squared squared is 16 is 1 mod 15. 13, should try 13. Well, it's actually 13 is easy. That's 13 is congruent to minus 2 mod 15. So 13 to the fourth power is minus 2 to the fourth power, which is 16, which is 1 mod 15. In fact, if we keep experimenting, playing around, what we'll see, in fact, that is, if A and 15 are relatively prime, A to a certain power is always congruent to 1 mod 15, but the power is not 14. In fact, the power of 4 works. So if A is relatively prime to 15, let's see, B of 15, this is the order 3 function. This is the number of integers relatively prime to 15. This is equal to 8. There are 4 numbers between 1 and 15 that are relatively prime to 15. They are 1, 2, 4, 7, 8, 11, and 13. 1, 2, not 3, 4, not 5 or 6, 7, 8, not 9 or 10, 11, 12, 13, and 14. So these are the 8 numbers that are relatively prime to 15, between 1 and 15. And every one of them raised to the fourth power is 1. So there is, as it turns out, something like Fermat's little theorem, not for primes, for products of 2 primes. And let me write it down and actually see if I can give a little proof of it right now. So in the book, this is theorem 3.1, which is called Euler's theorem, Euler's formula. for PQ. That means a number that is a product of two distinct primes, P and Q. So P and Q, distinct prime numbers. So a simple case says that if A is relatively prime to P and Q, so if the greatest common divisor of A and PQ is 1, then A to the power P minus 1, Q minus 1 is always congruent to 1 mod PQ. So for example, if M is 15, which is 3 times 5, so P equals 3, Q equals 5, M is a product of these two prime numbers. So P minus 1 times Q minus 1 is 2 times 4 is 8. So this would say that if A and 15 are relatively prime, then A to the 8th is congruent to 1 mod PQ. You can actually improve this, that in the sense that a smaller exponent works. Let G be the greatest common divisor of P minus 1 and Q minus 1. If the GCD of A and PQ is 1, then A to the power of P minus 1 times Q minus 1 divided by G is congruent to 1 mod PQ. And in our example, P is 3, Q is 5. The GCD of P minus 1 and Q minus 1 is the GCD of 3 minus 1 and 5 minus 1. That's the GCD of 2 and 4, which is 2. So P minus 1, Q minus 1 over 2 is 8 over 2, which is 4. And we recovered what we saw in our example, that if the greatest common divisor of A and 15 is 1, then A to the 4th is congruent to 1 mod 15. So actually, let's try and prove this result. Proof. So if the GCD of A and PQ is 1, that is, I mean, the only P and Q are prime, so the only divisor of PQ, the only divisors, 1, P, Q, and P times Q itself. And in particular, if A is relatively prime to P and Q, then the GCD of A and P and the GCD of A and Q are certainly both 1. So A to the P minus 1 is congruent to 1 mod P. By Fermat's little theorem. Which means if I take A to the P minus 1, Q minus 1 over G, this is the same as A to the P minus 1 raised to the integer power Q minus 1 over G, if G divides Q minus 1. This is 1 to the power. This is 1 mod P. And similarly, A to the Q minus 1 is 1 mod Q by Fermat's little theorem. So A to the P minus 1, Q minus 1 over G is A to the Q minus 1 raised to the power of P minus 1 over G, but this is just 1 to a power. This is congruent to 1 mod P. So if I look at this number minus 1 is divisible by P and by Q. They're distinct primes. So A to the P minus 1, Q minus 1 over G is congruent to 1 mod p. So that is Euler's formula for a number that is the product of 2 primes. Now, the Rsa crypto system is based on the following equation or congruence. So we're given a modulus n and integers, using positive integers, c and e. Compute or solve the congruence if you can. X to the e is congruent to c mod n. So we can think of it like this. X is like the eth root of c, right? Because if x to the e were c in the real numbers, or the complex numbers, then x would be the eth root of c. So this is like we're trying to take the eth root of a number with respect to some modulus. And the Rsa crypto system is based on the difficulty of this problem of taking roots. Now, in some sense, this is, I'll just say put in parentheses, in quotation marks, easy if n equal p is a prime number. And this is the content of proposition 3.2 in the text. So we start with a prime number p, a positive integer e greater than or equal to 1 is positive, such that the greatest common divisor of e and p minus 1 is 1. So by the extended Euclidean algorithm, we know there exists an inverse d, an integer d, such that d times e is congruent to 1 mod p minus 1. Which is a theorem we've seen. You can solve the congruence xe congruent to 1 mod p minus 1 uniquely if e and p minus 1 are relatively prime. And now the theorem says the following. If we want to find an eth root of a number c, the congruence x to the e congruent to c mod p has a unique solution. And the unique solution is exactly the following: x congruent to c to the d mod p. And the proof is really just one line. If I let x be c to the d, so x to the e is c to the d to the e. That's c to the power de by just the rules of exponents. de is 1 mod p minus 1. This says that de is 1 plus p minus 1 times some number k. So this is c to the 1 plus p minus 1 times k. which is C times C to the P minus 1 to the K. Now, of course, if C were 0 mod P, X would be 0. So if C is not 0 mod P, that means C and P are relatively prime. So C to the P minus 1 by Fermat's little theorem is congruent to 1 mod K, 1 mod P. Power of 1 is 1. This is C mod P. So if P is a prime, this congruence has a solution, and the solution is C to the D. And I can also show that it's unique. If X to the E and Y to the E are both congruent to C mod P, then if I raise things to powers, the congruence is preserved. X to the DE is congruent to Y to the DE mod P. But if DE is 1 plus P minus 1 times K, this is X and this is Y, again by Fermat's little theorem. So taking roots mod a prime is easy. There's a simple way to do it. The difficulty comes up when we have a product of 2 primes. So don't really want to consider the case X to the E congruent to C mod N when N is not a prime. N is equal to a product of P and Q, where P and Q are distinct, different prime numbers. And we're going to consider this in the case when E is a positive integer and the GCD of E and P minus 1 times Q minus 1 is 1. So this is proposition 3.5. We have distinct prime numbers P and Q, a positive integer E, which is relatively prime to P minus 1 and Q minus 1. If E is relatively prime to P minus 1 times Q minus 1, there exists an integer D such that D times E is congruent to 1 mod the product of P minus 1 times Q minus 1. So we know there's such a D. And the proposition says that the congruence X to the E congruent to C mod PQ has a unique solution. X is equal to C to the D mod PQ. We're going to prove it in the special case, but it's not what it says special. The GCD of C and PQ is equal to 1. So we use the fact that if A is relatively prime to PQ, prime to Q, so the GCD of A and PQ is 1, then A to the power of P minus 1, Q minus 1 is congruent to 1 mod PQ. This is the slight generalization of Fermat's-Little theorem that we called Euler's formula at the beginning of this talk. So suppose I let x equals c to the d. So x to the e is c to the d to the e is c to the de. De is congruent to 1 mod that product. So this is c to the 1 plus p minus 1 q minus 1 times some number k, which is congruent to c times c to the p minus 1 q minus 1 to the k. But this is 1. So x to the e is c. So x equals c to the d mod pq is the eth root of c. And we can prove it's unique by the same argument. If x to the e is congruent to y to the e mod pq, then x to the ed is congruent to y to the ed mod pq. But again, by the same argument, this is x and this is y. So it looks like it's easy to find the eth root of c mod pq, even though I started off by saying this is the basis of the crypto system that no one can break. So here's the idea of the crypto system. I want anyone to send me a message that is encrypted, and everyone can know how the encryption method works, but I'm the only person who can decrypt or decipher the message. So suppose let's say Alice, or the way the book sets it up, Bob chooses primes P and Q and multiplies them together and gets a number n, which is P times Q. Bob chooses an exponent, E, which is a number such that E, the greatest common divisor of E, and P minus 1, Q minus 1 are relatively prime. And Bob publishes N and E. And so everyone knows this pair of numbers, capital N and E. And the encryption method is given a plain text, the message you want to send, X, compute the number C, which is X to the E mod N. So I take my message that I want to send you, E, X, I raise it to the eth power reducive mod n, and I transmit or publish to the world C. This is my ciphertext. So we want to find X. So to find X, that is to decipher the message, we must solve the congruence, X to the E congruent to C mod n. We know the modulus n, we know the exponent E, and we know the ciphertext C. Find X. Well, I just described the way to do that. X is going to be C to the D mod n, where CD, D is an integer, such that CD is congruent to 1, mod P minus 1, Q minus 1. But to find D, I need to know P minus 1 and Q minus 1. That is, I need to know P and Q. I can only find P and Q by factoring n. If n is a big number with, let's say, a few thousand digits, I can't factor it. There's not enough computing power in the universe to factor a number, even if you know it's a product of 2 primes only. So calculating the decryption key, D, depends on factoring n. And I don't know how to factor n. I'm incapable. Everyone in the universe, as far as we know, is incapable of factoring n. So solving this congruence for X, it can't be done. And that provides the security in this so-called Rsa crypto system. Very important. And it's based on some simple number theory and just the difficulty of factoring. So I'll talk about that more in the next one.